Binary number.
In mathematics and digital electronics, a binary number is a number expressed in the binary numeral system, or base 2 numeral system, which represents numeric values using two different symbols, typically 0 and 1. More specifically, the usual base 2 system is a positional notation with a radix of 2. Because of his straightforward implementation in digital electronic circuitry using logic gates, the binary system is used internally by almost all modern computers and computer-based devices such as mobile phones.
History.
The modern binary number system was invented by Gottfried Leibniz in 1679 and appears in his article Explication de l'arithmétique binaire. The full title is translated into English as The Explanation of the Binary Arithmetic, which uses only the characters 1 and 0, with some remarks on its usefulness, and on the light it throws on the ancient Chinese figures of Fu Zai. 1703. Leibniz's system uses 0 and 1, like the modern binary numeral system. As a xenophile, Leibniz was aware of the Yijing, or I Ching, and noted with fascination how its hexagrams correspond to the binary numbers from 0 to 111,111, and concluded that this mapping was evidence of major Chinese accomplishments in the sort of philosophical mathematics he admired. Leibniz was first introduced to the I Ching through his contact with the French Jesuit Joachim Bouvet, who visited China in 1685 as a missionary. Leibniz saw the I Ching hexagrams as an affirmation of the universality of his own religious beliefs as a Christian. Binary numerals were central to Leibniz's theology. He believed that binary numbers were symbolic of the Christian idea of creatio ex nihilo, or creation out of nothing. Binary systems predating Leibniz also existed in the ancient world. The aforementioned I Ching that Leibniz encountered dates from the 9th century BC in China. The binary system of the I Ching, a text for divination, is based on the duality of yin and yang. Leibniz interpreted the hexagrams as evidence of binary calculus. He said that this arithmetic by 0 and 1 is found to contain the mystery of the lines of an ancient king and philosopher named Fui, who is believed to have lived more than 4,000 years ago, and whom the Chinese regard as the founder of their empire and their sciences. The text contains a set of 8 trigrams, Bagua, and a set of 64 hexagrams, 64 Gui, analogous to the 3-bit and 6-bit binary numerals, were in use at least as early as the Zhou dynasty of ancient China. Leibniz theorized that Pope Sylvester II introduced binary numbers to Europe from Asia through Moorish intermediaries in Spain. An example of Leibniz's binary numeral system is as follows. The residents of the island of Mangarval in French Polynesia were using a hybrid binary decimal system before 1450. Slit drums with binary tones are used to encode messages across Africa and Asia. The Indian scholar Pingala, around 5th–2nd centuries BC, developed a binary system for describing prosody. He used binary numbers in the form of short and long syllables, the latter equal in length to 2 short syllables, making it similar to Morse code. Pingala's Hindu classic titled Chandasastra, 8.23 describes the formation of a matrix in order to give a unique value to each meter. The binary representations in Pingala's system increases towards the right, and not to the left like in the binary numbers of the modern, Western positional notation. In the 11th century, scholar and philosopher Shaoyong developed a method for arranging the hexagrams which corresponds, albeit unintentionally, to the sequence 0 to 63, as represented in binary, with yin as 0, yang as 1 and the least significant bit on top. The ordering is also the lexicographical order on sextuples of elements chosen from a 2-element set. Similar sets of binary combinations have also been used in traditional African divination systems such as Ifa as well as in medieval Western geomancy. The base 2 system utilized in geomancy had long been widely applied in sub-Saharan Africa. In 1605 Francis Bacon discussed a system whereby letters of the alphabet could be reduced to sequences of binary digits, which could then be encoded as scarcely visible variations in the font in any random text. Importantly for the general theory of binary encoding, he added that this method could be used with any objects at all, provided those objects be capable of a twofold difference only. As by bells, by trumpets, by lights and torches, by the report of muskets, and any instruments of like nature. See Bacon's cipher. In 1854, British mathematician George Boole published a landmark paper detailing an algebraic system of logic that would become known as Boolean algebra. His logical calculus was to become instrumental in the design of digital electronic circuitry. In 1937, Claude Shannon produced his master's thesis at MIT that implemented Boolean algebra and binary arithmetic using electronic relays and switches for the first time in history. Entitled A Symbolic Analysis of Relay and Switching Circuits, Shannon's thesis essentially founded practical digital circuit design. In November 1937, George Stibitz, then working at Bell Labs, completed a relay-based computer he dubbed the Model K, for kitchen, where he had assembled it, which calculated using binary addition. Bell Labs thus authorized a full research program in late 1938 with Stibitz at the helm. Their complex number computer, completed January 8, 1940, was able to calculate complex numbers. In a demonstration to the American Mathematical Society conference at Dartmouth College on September 11, 1940, Stibitz was able to send the complex number calculator remote commands over telephone lines by a teletype. It was the first computing machine ever used remotely over a phone line. Some participants of the conference who witnessed the demonstration were John von Neumann, John Mauchly and Norbert Wiener, who wrote about it in his memoirs.
Representation.
Any number can be represented by any sequence of bits, binary digits, which in turn may be represented by any mechanism capable of being in two mutually exclusive states. Any of the following rows of symbols can be interpreted as the binary numeric value of 667. The numeric value represented in each case is dependent upon the value assigned to each symbol. In a computer, the numeric values may be represented by two different voltages. On a magnetic disk, magnetic polarities may be used. A positive, yes, or on state is not necessarily equivalent to the numerical value of 1. It depends on the architecture and use. In keeping with customary representation of numerals using Arabic numerals, binary numbers are commonly written using the symbols 0 and 1. When written, binary numerals are often subscripted, prefixed or suffixed in order to indicate their base, or radix. The following notations are equivalent. When spoken, binary numerals are usually read digit by digit, in order to distinguish them from decimal numerals. For example, the binary numeral 100 is pronounced 100, rather than 100, to make its binary nature explicit, and for purposes of correctness. Since the binary numeral 100 represents the value 4, it would be confusing to refer to the numeral as 100, a word that represents a completely different value, or amount. Alternatively, the binary numeral 100 can be read out as 4, the correct value, but this does not make its binary nature explicit.
Counting in binary.
Counting in binary is similar to counting in any other number system. Beginning with a single digit, counting proceeds through each symbol, in increasing order. Before examining binary counting, it is useful to briefly discuss the more familiar decimal counting system as a frame of reference.
Decimal counting.
Decimal counting uses the 10 symbols 0 through 9. Counting primarily involves incremental manipulation of the low-order digit, or the rightmost digit, often called the first digit. When the available symbols for the low-order digit are exhausted, the next higher-order digit, located one position to the left, is incremented, and counting in the low-order digit starts over at 0. In decimal, counting proceeds like so. After a digit reaches 9, an increment resets it to 0 but also causes an increment of the next digit to the left.
Binary counting.
In binary, counting follows similar procedure, except that only the two symbols 0 and 1 are used. Thus, after a digit reaches 1 in binary, an increment resets it to 0 but also causes an increment of the next digit to the left. Since binary is a base 2 system, each digit represents an increasing power of 2, with the rightmost digit representing 20, the next representing 21, then 22, and so on. To determine the decimal representation of a binary number, simply take the sum of the products of the binary digits and the powers of 2 which they represent. For example, the binary number 100,101 is converted to decimal form as follows. To create higher numbers, additional digits are simply added to the left side of the binary representation.
Fractions.
Fractions in binary only terminate if the denominator has 2 as the only prime factor. As a result, 1/10 does not have a finite binary representation, and this causes 10x 0.1 not to be precisely equal to 1 in floating point arithmetic. As an example, to interpret the binary expression for 1/3 equals 0.010101. This means, 1/3 equals 0 times 2. 1 plus 1 times 2. 2 plus 0 times 2. 3 plus 1 times 2. 4 plus equals 0.3125 plus. An exact value cannot be found with a sum of a finite number of inverse powers of 2, the zeros and ones in the binary representation of 1/3 alternate forever.
Binary arithmetic.
Arithmetic in binary is much like arithmetic in other numeral systems. Addition, subtraction, multiplication, and division can be performed on binary numerals.
Addition.
The simplest arithmetic operation in binary is addition. Adding two single-digit binary numbers is relatively simple, using a form of carrying. Adding two one digits produces a digit 0, while 1 will have to be added to the next column. This is similar to what happens in decimal when certain single-digit numbers are added together. If the result equals or exceeds the value of the radix, 10, the digit to the left is incremented. This is known as carrying. When the result of an addition exceeds the value of a digit, the procedure is to carry the excess amount divided by the radix, that is, 10/10, to the left, adding it to the next positional value. This is correct since the next position has a weight that is higher by a factor equal to the radix. Carrying works the same way in binary. In this example, two numerals are being added together, 011012, 1310, and 101,112, 2310. The top row shows the carry bits used. Starting in the rightmost column, 1 plus 1 equals 102. The 1 is carried to the left, and the 0 is written at the bottom of the rightmost column. The second column from the right is added, 1 plus 0 plus 1 equals 102 again. The 1 is carried, and 0 is written at the bottom. The third column, 1 plus 1 equals 112. This time, a 1 is carried, and a 1 is written in the bottom row. Proceeding like this gives the final answer 1,001,002, 36 When computers must add two numbers, the rule that x or y equals x plus y, mod 2 for any two bits x and y allows for very fast calculation, as well.
Long carry method.
A simplification for many binary addition problems is the long carry method or Brookhouse method of binary addition. This method is generally useful in any binary addition where one of the numbers contains a long string of ones. It is based on the simple premise that under the binary system, when given a string of digits composed entirely of n ones, where n is any integer length, adding 1 will result in the number 1 followed by a string of n zeros. That concept follows, logically, just as in the decimal system, where adding 1 to a string of n nines will result in the number 1 followed by a string of n zeros. Such long strings are quite common in the binary system. From that one finds that large binary numbers can be added using two simple steps, without excessive carry operations. In the following example, two numerals are being added together, 11101111102, 95,810, and 10101100112, 69,110, using the traditional carry method on the left, and the long carry method on the right. The top row shows the carry bits used. Instead of the standard carry from one column to the next, the lowest ordered one with a 1 in the corresponding place value beneath it may be added and a 1 may be carried to one digit past the end of the series. The used numbers must be crossed off, since they are already added. Other long strings may likewise be cancelled using the same technique. Then, simply add together any remaining digits normally. Proceeding in this manner gives the final answer of 110011100012, 164,910. In our simple example using small numbers, the traditional carry method required 8 carry operations, yet the long carry method required only 2, representing a substantial reduction of effort.
Addition table.
The binary addition table is similar, but not the same, as the truth table of the logical disjunction operation. The difference is that, while
Subtraction.
subtraction works in much the same way. Subtracting a 1 digit from a 0 digit produces the digit 1, while 1 will have to be subtracted from the next column. This is known as borrowing. The principle is the same as for carrying. When the result of a subtraction is less than 0, the least possible value of a digit, the procedure is to borrow the deficit divided by the radix, that is, 10/10, from the left, subtracting it from the next positional value. Subtracting a positive number is equivalent to adding a negative number of equal absolute value. Computers use sign number representations to handle negative numbers, most commonly the 2's complement notation. Such representations eliminate the need for a separate subtract operation. Using 2's complement notation, subtraction can be summarized by the following formula. A. B equals A plus not B plus 1.
Multiplication.
Multiplication in binary is similar to its decimal counterpart. Two numbers A and B can be multiplied by partial products. For each digit in B, the product of the digit in A is calculated and written on a new line, shifted leftward so that its rightmost digit lines up with the digit in B that was used. The sum of all these partial products gives the final result. Since there are only 2 digits in binary, there are only 2 possible outcomes of each partial multiplication. If the digit in B is 0, the partial product is also 0. If the digit in B is 1, the partial product is equal to A. For example, the binary numbers 1011 and 1010 are multiplied as follows. Binary numbers can also be multiplied with bits after a binary point. See also Booth's multiplication algorithm.
Multiplication table.
The binary multiplication table is the same as the truth table of the logical conjunction operation.
Division.
Binary division is again similar to its decimal counterpart. Here, the divisor is 1012, or 5 decimal, while the dividend is 110,112, or 27 decimal. The procedure is the same as that of decimal long division. Here, the divisor 1012 goes into the first 3 digits 1102 of the dividend one time, so a 1 is written on the top line. This result is multiplied by the divisor, and subtracted from the first 3 digits of the dividend. The next digit, a 1, is included to obtain a new 3-digit sequence. The procedure is then repeated with a new sequence, continuing until the digits in the dividend have been exhausted. Thus, the quotient of 110,112 divided by 1012 is 1012, as shown on the top line, while the remainder, shown on the bottom line, is 102. In decimal, 27 divided by 5 is 5, with a remainder of 2.
Square root.
Binary square root is similar to its decimal counterpart too. But, it's simpler than that in decimal. For example,
Bitwise operations.
though not directly related to the numerical interpretation of binary symbols, sequences of bits may be manipulated using Boolean logical operators. When a string of binary symbols is manipulated in this way, it is called a bitwise operation. The logical operators and, or, and XOR may be performed on corresponding bits in two binary numerals provided as input. The logical NOT operation may be performed on individual bits in a single binary numeral provided as input. Sometimes, such operations may be used as arithmetic shortcuts, and may have other computational benefits as well. For example, an arithmetic shift left of a binary number is the equivalent of multiplication by a positive integral power of 2.
Conversion to and from other numeral systems. Decimal.
To convert from a base 10 integer numeral to its base 2 binary equivalent, the number is divided by 2, and the remainder is the least significant bit. The integer result is again divided by 2, its remainder is the next least significant bit. This process repeats until the quotient becomes 0. Conversion from base 2 to base 10 proceeds by applying the preceding algorithm, so to speak, in reverse. The bits of the binary number are used one by one, starting with the most significant, leftmost, bit. Beginning with the value 0, repeatedly double the prior value and add the next bit to produce the next value. This can be organized in a multi-column table. For example, to convert 100,101,011,012 to decimal, the result is 119,710. Note that the first prior value of 0 is simply an initial decimal value. This method is an application of the Horner's scheme. The fractional parts of a number are converted with similar methods. They are again based on the equivalence of shifting with doubling or halving. In a fractional binary number such as 0.110101101012, the first digit is, the second, etc. So if there is a 1 in the first place after the decimal, then the number is at least, and vice versa. Double that number is at least 1. This suggests the algorithm, repeatedly double the number to be converted, record if the result is at least 1, and then throw away the integer part. For example, 10, in binary, is. Thus the repeating decimal fraction 0.3 is equivalent to the repeating binary fraction 0.01. Or for example, 0.110, in binary, is. This is also a repeating binary fraction 0.00011. It may come as a surprise that terminating decimal fractions can have repeating expansions in binary. It is for this reason that many are surprised to discover that 0.1 plus 0.1, 10 additions, differs from 1 in floating point arithmetic. In fact, the only binary fractions with terminating expansions are of the form of an integer divided by a power of 2, which 1/10 is not. The final conversion is from binary to decimal fractions. The only difficulty arises with repeating fractions, but otherwise the method is to shift the fraction to an integer, convert it as above, and then divide by the appropriate power of 2 in the decimal base. For example, another way of converting from binary to decimal, often quicker for a person familiar with hexadecimal, is to do so indirectly, first converting, in binary, into, in hexadecimal, and then converting, in hexadecimal, into, in decimal. For very large numbers, these simple methods are inefficient because they perform a large number of multiplications or divisions where one operand is very large. A simple divide-and-conquer algorithm is more effective asymptotically. Given a binary number, it is divided by 10k, where k is chosen so that the quotient roughly equals the remainder. Then each of these pieces is converted to decimal and the two are concatenated. Given a decimal number, it can be split into two pieces of about the same size, each of which is converted to binary, whereupon the first converted piece is multiplied by 10k and added to the second converted piece, where k is the number of decimal digits in the second, least significant piece before conversion.
Hexadecimal.
Binary may be converted to and from hexadecimal somewhat more easily. This is because the radix of the hexadecimal system, 16, is a power of the radix of the binary system, 2. More specifically, 16 equals 24, so it takes 4 digits of binary to represent 1 digit of hexadecimal, as shown in the table to the right. To convert a hexadecimal number into its binary equivalent, simply substitute the corresponding binary digits. To convert a binary number into its hexadecimal equivalent, divide it into groups of 4 bits. If the number of bits isn't a multiple of 4, simply insert extra 0 bits at the left, called padding. For example, to convert a hexadecimal number into its decimal equivalent, multiply the decimal equivalent of each hexadecimal digit by the corresponding power of 16 and add the resulting values.
Octal.
Binary is also easily converted to the octal numeral system, since octal uses a radix of 8, which is a power of 2, namely, 23, so it takes exactly 3 binary digits to represent an octal digit. The correspondence between octal and binary numerals is the same as for the first 8 digits of hexadecimal in the table above. Binary 000 is equivalent to the octal digit 0, binary 111 is equivalent to octal 7, and so forth. Converting from octal to binary proceeds in the same fashion as it does for hexadecimal. And from binary to octal. And from octal to decimal.
Representing real numbers.
Non-integers can be represented by using negative powers, which are set off from the other digits by means of a radix point, called a decimal point in the decimal system. For example, the binary number 11.012 thus means, for a total of 3.25 decimal. All dyadic rational numbers have a terminating binary numeral. The binary representation has a finite number of terms after the radix point. Other rational numbers have binary representation, but instead of terminating, they recur, with a finite sequence of digits repeating indefinitely. For instance, the phenomenon that the binary representation of any rational is either terminating or recurring also occurs in other radix-based numeral systems. See, for instance, the explanation in decimal. Another similarity is the existence of alternative representations for any terminating representation, relying on the fact that 0.111111 is the sum of the geometric series 2. 1 plus 2. 2 plus 2. 3 plus. Which is 1. Binary numerals which neither terminate nor recur represent irrational numbers. For instance, 0.101010000000100000000000. Those have a pattern, but it is not a fixed-length recurring pattern, so the number is irrational. 1.011001000000000010001100011101110 is the binary representation of the square root of 2, another irrational. It has no discernible pattern. See irrational number.